Hello, we're here in the fifth week of the fifth chapter. We are in section 1, but this chapter mostly deals with polynomials and rational functions, and we're going to be talking about polynomial inequalities and rational inequalities to kind of wrap this chapter up. So, as I said, we're in section 1, we are talking about polynomial functions. So let's begin. Okay. Well, this is just to kind of recap what I just said. These are the things we're to be talking about: polynomial functions, rational functions, and their inequalities. And we're going to be also graphing them as well. So let's get started. So identifying polynomial functions and their degree. Alrighty. So what is a polynomial function? A polynomial function is one variable is a function of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way out to a sub 1 x plus a sub 0. Now that looks very, very complicated. With all these little a subs, a sub n minus 1, all those are just the coefficients. What that basically means is those are just real numbers. So when we were dealing with quadratic functions, if you remember, it was ax squared plus bx plus c, where a, b, and c are real numbers. Well, a quadratic function has three terms typically, ax squared, the bx, and the c. So since there was only three terms, we could have named them a, b, and c, sure. But when a polynomial is bigger than degree 2, like degree, let's say, 20, that would have 21 terms. And you'd almost run out of letters in the alphabet if you just use the ax to the 20th, bx to the 19th, and so on down the line. You eventually might run out of letters if you surpass 26 characters, because there's 26 letters in the alphabet. So what they do to fix that is they use these little a subs. So if you notice, a sub n, x to the n. So if you have an x to the 20th term in there, then it would be a sub 20, x to the 20th, plus a sub 19, x to the 19th. That way you never run out of letters, because the subscript, the a sub 20, it takes on the value of the a sub 19 is like the b, and so on down the line. So that way you never run out of letters, plus and it's easier to characterize which one goes with which term. For example, if I said, well, what is the coefficient of the x to the 13th term? Well, then it would be a sub 13. Otherwise, if you just use a, b, and c, you'd have to count down 13 letters in the alphabet to match it up with that x to the 13th term. And so that can get kind of confusing. And so the a subs, they're not to be scared about. They're just basically real numbers. So, and these are called constants. They're called the coefficients of the polynomial. N is greater than or equal to 0 is an integer, and x is a variable. If a sub n does not equal 0, it is called the leading coefficient, and n is the degree of the polynomial. So the polynomial is basically the largest degree. So if you have an x to the 15th, an x to the 11th, and x to the 12th term, then x to the 15th is the largest one, so 15 is the degree of the polynomial. So quite easily, I figured out. The domain of a polynomial function is a set of all real numbers, which is kind of nice, because that means if you have a polynomial function, you can put anything in to get anything out. So you're not set, okay, on what you can and cannot put in. You can put any value in. So the set is all real numbers. So what we're going to do in this example is we're going to identify polynomial functions. So there's 1, 2, there's like a, b, c, all the way out to f. And some of these will be polynomials and some of them will not, okay? And if they are polynomial, for those that are, we're going to write them in standard form, and we're going to identify the leading term and the constant term as well. So let's look at the first one. P of x is equals to 5x squared minus 1/4, 5x to the third minus 1/4 x squared minus 9. Okay, so P of x is a polynomial function of degree 3, because the 3 is the largest exponent, and it is already in standard form. Now you're like, well, why wouldn't it be in standard form? Well, it's in standard form because it's in the a sub n x to the nth term. So the coefficients are 5, negative 1/4, and technically negative 9. So we're already in standard form. The leading term is 5x to the third, and the constant term is negative 9, very easily. And something they do not ask here, well, what's the degree of the polynomial? Oh, it did say the degree of the polynomial is 3. It did say that. So the degree is 3. The leading term is 5x to the third, and the constant term is negative 9. So what we're here, we're just kind of getting familiar with polynomials. Not doing anything fancy. We're just kind of trying to be able to identify what is and what is not a polynomial. That's all this example is about. All righty. So the next one is f of x equals x plus 2, okay, minus, what is that, 3x to the fourth. Yes, okay. So first of all, the degree is 4 because that's the largest exponent. Standard form, notice they rearranged the terms, the negative 3x to the fourth plus x plus 2. So we have to put it from the largest degree to the smallest degree. Okay, so the leading term is negative 3x to the fourth, and the constant term is 2. Let's talk a little bit more about the constant term. The constant term is the term that never changes. Well, the only time it will never change is when it doesn't have a variable attached to it. So the constant is the one without the variable attached. Sometimes the constant term is 0 because there isn't one of those. But the 2 is the only one that does not have an x attached to it. So 2 is the constant term. Okay? Let's look at the next one. G of x is the square root of x. And this is not a polynomial because the square root of x is x to the 1/2. And the exponent is 1/2. Square root of x is x to the 1/2. So the variable x is raised to the 1/2 power, which is not a non-negative integer. So by definition of a polynomial, the exponents have to be non-negative integers by the definition on the previous slide. And 1/2 is definitely not an integer. It is non-negative, but it's not an integer. So if you're dealing with a square root of x anywhere in a function, it could be a function, but it's not a polynomial function. Now let's click the next one. This one is not a polynomial either. It is a ratio of two distinct polynomials. The numerator and the denominator are both polynomials, but the ratio of them, when you divide them out, is not a polynomial. Actually, it's called something else. We'll talk a little bit more about this in Chapter 5 as well, and it's called a rational function. And that comes a little bit later in 5.2 and actually in 5.3 as well. So this is not a polynomial function. All righty? All right. Now let's look at this one. G of x is equals to 8. Now, yeah, well, this can't be a polynomial, right? Well, look at it. It's got a non-zero constant polynomial function. So 0 is the degree of that is the degree of 0. So what that basically means is that this function has no variable x. So if you want to get technical, 8 is 8x to the 0, which makes it 0 degree. I look at it this way. If there is no variable, then the degree is 0. So 8 is the constant term, it's the leading term, it's the only term. So the polynomial is in standard form. The leading term and the constant term are both 8 because it's only got one term in it. So probably the easiest of all polynomials. And then f, okay, h of x is equals to negative 2, what is that? X to the third times x minus 1 quantity squared. Now, you're like, well, is this, you looked at the two problems previous to that, the ratio of two polynomials, and it wasn't a polynomial. But what about the product? You know, the negative 2x to the third, that is definitely a polynomial. X minus 1 squared is a polynomial if you FOIL it out. But what about the product of them? Well, if you multiply them out, and multiply them out again, you get negative 2x, oh goodness, negative 2x to the fifth plus 4x to the fourth minus 2x to the third. Now, that's expanded out. Every term is got a non-negative integer as an exponent. They have coefficients, so indeed this is a polynomial. And the degree turns out to be 5 because that's the highest degree once you multiply it out. And so that is a polynomial, and the leading term is the first one, negative 2x to the fifth. Now what about the constant term? There is no constant. The negative 2x to the third was the last term in this expansion. But there is no term that's just sitting out there without variable. So in that case, the constant is 0. Okay? Now, the question is, can you find the degree without multiplying it out? Could we do that? Can we figure out what the degree of this thing is without actually doing the product? I think you can. If you just kind of look at it this way, the x squared, x minus 1 squared, when you know when you multiply that out, it's going to be x times x, which is x squared. And then you're going to have to end up multiplying the negative 2x to the third times that, so x to the third times x to the second is x to the fifth. So the degree would have to be 5. So you can actually identify the degree without carrying out the whole multiplication. So you look at each factor and then add up the degrees. So the first factor is negative 2x to the third, that's 3. And when you have x minus 1 squared, when you multiply it out, it'd be x squared, so that's 2, and 2 and 3 is 5. So the degree is 5. Okay? So let's move on. Okay, these are a table giving you the different possibilities of a degree. No degree, f of x equals 0. 0, it's a 0 function, it's the x-axis. If you have 0, f of x equals a sub 0, which a sub 0 equals 0 is the constant function, and it's the horizontal line with the y-intercept a sub 0. And then you have f of x equals a sub 1 x plus a sub 0. A does not equal 0. That's a linear function. We've talked about that back in chapter 2, okay, when we talked about linear functions, and actually 2.3. Now, it wasn't called a sub 1 x plus a sub 0. It was called mx plus b, right? Yeah, it was. But the a sub 1 in this case was the m, and the b is now going to be the a sub 0. So they're using different letters to identify the same thing, but they want to be consistent with how they define polynomials, and so that's why they're not using mx plus b here. They're using a sub 1 and a sub 0. Okay? But that's the linear function. And remember, when we got down to the quadratic functions, it was ax squared plus bx plus c, and that was in chapter 3. And but here they're using a sub 2 x squared instead of the a sub 1 x to the first instead of the bx, and then plus a sub 0 instead of the c. So it's the same thing but using different letters, and that's the quadratic function. So they gave you these three, and this one's, the graph is called a parabola, of course. And they gave you these because they know you've talked about these already. The linear function, the quadratic function, and when the degree is 0, that was the horizontal line. And that was also in chapter 2.3 when we were talking about horizontal lines. And so they know you've already talked about these, but they wanted to show you, this is what it would look like, in this context. Okay? So, all right, let's look at these graphs. Okay? Now, the first graph is a graph of a polynomial function, but the second one is not. You're like, well, how do you know? Well, polynomial functions are smooth. They don't come to a point. They have no corner points, and we call those corner points cusp, C-U-S-P, and there's no gaps. In other words, it's continuous from one side of the graph to the other graph side. You don't have to lift your pencil to go from one end to the other. But look at the second one. Not only does it have a cusp, it has several of them, but it also has a gap, and it also has something else called a hole. Now, we actually call that a removable discontinuity. That's what that's called. A hole that's the slang term for what the mathematicians would call a removable discontinuity. That's a hole. But polynomials don't have any of those things. They don't have gaps, they don't have holes, and they don't have cusp. They're smooth, they're rounded, and they're continuous. So the left one is a polynomial, the right one is not. Now let's look at the power function of degree n. It is a monomial function of the form f of x equals a sub n x to the n. Okay? Where a is the real number, a does not equal 0, and n is... In other words, this is basically the first term in the expansion of we had before. So since there was only, this one's only going to be one term, they don't put the a sub n. They just let it be a. They could have very well let it be said a sub n x to the n. But since there's not going to be more terms anyway, they're being a little lazy here, as a matter of fact. They call it a times x to the n. It's the first term of a polynomial expansion is called the power function. Now, believe it or not, we have actually graphed a few power functions already in the library functions. So we've already done those. We did an x to the second, we did x to the third, we did x to the fourth, and I think we've even done x to the fifth in the power functions. So we have done those already, okay? So there's nothing new here. But the reason we're going to put it back in and talk about it again right here is because of something called the end behavior. And we'll talk about the end behavior when it's time to start graphing the polynomials, which is coming up, okay? So let's look at some power functions. So we have the first one. It's f of x equals x to the n when n is greater than or equal to 4. And so if you look at the first one, it's y equals x squared, the black one, and then look at x to the fourth. And then look at the second graph. The x to the fourth is there, and then look at x to the eighth. The bigger the even number is, the sharper up it looks, but they all have the same characteristic. They all go up. Both of the extremes go up. That's what we call the end behavior, E-N-D B-E-H-A-V-I-O-R, end behavior. So that's what they do. So, but that's what power functions look like. But here's the coolness of this. On polynomial functions, remember all those curves I was showing you a while ago that I said they were smooth and they're rounded edges and everything else, and you go from one end to the other end? If you go back and look at that again, let's go back and look at it. See this one right here? They're all smooth and they're rounded, but look at the very extremes. They both go up on both ends. Now, I don't know much about this polynomial, but I do know something about it. The end behavior shows me the degree of the polynomial. It's an even degree. It's not 2, but it is even. Okay, so it could be 6 or 8 or 10 or something like that, but it's an even degree polynomial because both ends go up. So if we looked at, so those go up, the one previous that went up, so they both have even degree. Those other things, those curved around, those are called turning points. We'll talk a little bit about that as well. So anyway, so it says f is an even function, so the graph is symmetrical to the y-axis, as you can see. The domain is a set of all real numbers, just like all polynomials are. The range is a set of non-negative real numbers because it starts at 0 and it goes up. That's what power functions do. Okay? The graph always contains the point -1, 1, 0, 0, 1, 1. If you notice all those 4 graphs that are on there, you're seeing that, they all have those characteristics. As an exponent n increases in magnitude, the graph is steeper when x is less than 1, when x is greater than 1, as you can see. Okay, but as you go through the origin, it flattens out a little bit more. So that's the shape that it has. Now, that's what they do. Now, this in itself, if this is all it was, we probably wouldn't be talking about it. But they wanted to introduce this here, so when we start talking about the polynomial functions, you'll know what that end behavior is. And that's what I'm going to relate this to a little bit later. Okay, let's look at the odd functions. The figures of odd functions, so x to the third and x to the, this one's going to be an x to the nth graph when n is odd. Okay. Now look at x to the 5th. It comes a little sharper and flattens out a little bit closer as you between -1 to 1. But notice the idea that they do. The x to the 2nd, the x to the 4th, and x to the 6th, they all went the same direction. The odd ones are going in opposite direction. Okay? And so this is some properties. They're symmetrical to the origin, which basically means if you turn the picture upside down, it would look the same. If you rotate it 180 degrees, in other words, it looks the same picture. The domain, the range is a set of all real numbers. They go through -1, -1, 0, 0, 1, 1. And then as the exponent increases, it becomes steeper as x is between less than 1 and greater than 1, x less than -1 and x is greater than 1. But as you're close to origin, it flattens out. Okay? But again, that in itself would not be probably a reason we would even talk about that in this course. It's the end behavior. That's why I'm trying to plant that seed here. So when we start graphing polynomials, and I say, oh, you remember the power function. So this one's an odd one. So the left arm will go down, the right arm will go up. Or if it was an even function, they both go up in the same direction. Now this is assuming we have a leading coefficient that's positive. Okay? If that leading coefficient is negative in this case, the left arm would go up and the right arm goes down. Why do you think that would happen? Yeah, because the negative out front gives you a vertical reflection, right? So the negative out front gives that vertical reflection. So in this case, the left arm would go up and the right arm would go down if in the case that there's a negative in the leading term. Whereas when they're even degree with a negative out front, what would happen then, you think? Yep, they both go down in the same, they both end up going in the same direction. So you can tell a little bit about the polynomial by looking at its graph. You can have as many, turning points as you want. This is what we call like little local extrema as you want. But you can tell us something about their degree just by looking at the ends of the graph. So you can have a lot of turning points, and then both ends will go up. Oh, it's got an even degree. Or have a lot of turning points and they both go down. Oh, it's an even degree, but it has a leading coefficient that's negative. So that's very important as we come up, which I think is coming up pretty soon. Okay? So that concludes this video. If you have any questions, as always, you let me know and we'll try to get those questions answered for you. And as always, have a good day.